Good morning, all of you. Today, we are going to discuss the topic locating tetrahedral and octahedral voids in face centered cube FCC. Locating tetrahedral and octahedral voids in a unit cell of FCC. In FCC, there are four atoms at the corners, each contributing 1 by 8 to the unit cell. So, corner contribution is only 1, and from the face centers altogether 3. There are 6 faces. Face center means each atom will be contributing half half of that ball, half of that atom to that unit cell. So from the face contribution, 3 atoms, from the corner contribution, 1 atom. So altogether, 4 atoms are present in a unit cell. We know that if n atoms are present, then the number of tetrahedral voids will be twice n. If 4 atoms are present, then the number of tetrahedral voids will be 8. If 4 atoms are present, the number of tetrahedral voids will be 8, that is double. If you're going to find out the number of octahedral voids, then it will be 4 only. If n is the number of atoms with which the crystal lattice is made, the number of octahedral voids will be the same, that is n. If 4 atoms are present in that unit cell, then there will be 4 octahedral voids. Let's see where is the location. Where are these octahedral voids and these tetrahedral voids? For that, I'm going to draw an FCC crystal lattice. This cube is divided into two FCC unit cell only. This is FCC. So each corners bigger atoms are present. So I'm going to show the bigger atoms at each corner. Corner, 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 all the 8 corners. And also the center of each face. Top face, side face, bottom face, this side face, and the back face. Now, where is the position of tetrahedral void? You can see there are 8 small cubes. 8 small cubes in the sense this is front, bottom, right. This one. This one is front, bottom, right. Like that. Back, bottom, right. Similarly, you can see there are 8 small cubes. This FCC, this this FCC unit cell, I have divided this FCC unit cell into 8 small cubes. Center of each small cube is a tetrahedral void. How it becomes a tetrahedral void? Let's see the void which is filled by a small atom. A small atom, a cation, is fitted over there. Now, how this become a tetrahedral void? This atom is in touch, is in contact with 4 atoms of this unit cell. One is this blue one is this blue one. So I'm going to draw a line. A line to this. It is in touch. Now, which is closer to the observer? I am the observer, or one who is looking at this diagram is the observer. Which one, black or blue? Which one is closer to the observer? Blue. So I'll be broadening that line towards that blue. This is in contact with this black. This black is in contact with this front face center, which is more closer to me, again blue only. So I'll be drawing a line in such a way that the line is broadened towards that blue. The black ball, the black atom, that tetrahedral void is in contact with this fellow also, this side face center. So I'll be drawing a line in such a way that the closer atom, which is more closer one is the black one. So I'll be drawing a line, means a wedge which is broadened, a wedge which is broadened towards that black atom. And this black center one is in contact with the bottom face center atom also, which is more closer. This black or blue, black only. So I'll be making a wedge, solid wedge, so that it is broadened towards that black atom. To make that atom visible, I'm so this is that yellow color, that yellow space is that tetrahedral void. Similar to this yellow spot, yellow ball, yellow atom, you can visualize 8 tetrahedral voids. There are 8 cubes, each center of the cube. Each center is a tetrahedral void. We know that there are 4 blue atoms. There are 4 blue atoms. So the number of tetrahedral voids will be double, that is 8. 8 tetrahedral voids. Now let's see one example. Each blue atom, I'm writing it as sulfide ion, S2 minus, S di positive, S di positive, S2 minus, S2 minus. So all blue atoms are S2 minus. And the tetrahedral voids, not all tetrahedral voids, only alternate tetrahedral voids are filled by Zn2 plus. So the molecule is zinc sulfide. Molecule is zinc sulfide. There are S2 minus how many? 4. There are 8 tetrahedral voids, but all the tetrahedral voids are not filled by Zn2 plus. Only alternate tetrahedral voids are filled by Zn2 plus. So instead of those 8 tetrahedral voids, only 4 zinc 2 plus, zinc 2 plus occupy, zinc 2 plus ions occupy only 4 tetrahedral voids in the crystal. So Zn4 S4, 4 4 get cancelled. The molecular formula will be written as ZnS. Unity cell properties are the properties of the entire crystal. This is only a unity cell. Such so many unit cells are kept together over and over, again and again in different directions to get the entire crystal lattice. So what is the formula derived? What is the molecular formula derived from this unit cell? ZnS. So the molecular formula of zinc sulfide is ZnS. In some cases, all the tetrahedral voids are filled. In that case, the molecular formula will be changing. Here we are visualizing only the location of tetrahedral voids. A unit cell, FCC unit cell, is divided into 8 small cubes, and center of each cube is a tetrahedral void. Now let's go for octahedral void. Where are the locations of this octahedral void? Again, I'm taking FCC only. In FCC, in your syllabus, locating octahedral voids in FCC. You know that the number of octahedral voids in a crystal lattice is the same as the number of the atoms with which the crystal lattice is made. So, we are going to FCC and we'll be seeing where are the locations of these octahedral voids. This is FCC. The typical example for this is sodium chloride. You know that the crystal lattice or this unit cell is made up of Cl minus ions, that is anion. Cl minus ion is anion. So size of Cl minus, bigger atoms or bigger ions or bigger particles make this lattice, crystal lattice. Now, the position, what you are seeing here, look at this position, this gap, this void. This void is in contact with, see, the line shows the contact. The void is in contact with this face center, side face center, this side face center, front face center, back face center, top face center, and bottom face center. So this void, this gap, it is in contact with, gap means that can be occupied by this Na plus, small Na plus, small cation will be occupying this position. So this cation Na plus will be in contact with how many anions? 6 anions. So we say its coordination number of this cation is 6. And since this is in contact with 6 anions, we say this is an octahedral void. This octahedral void's contribution to this particular unit cell, is 1, since it is the interior, since it is present in the interior of this FCC unit cell. So this is an octahedral void. Its coordination number is 6 because it is in contact with 6 other ion. If this is Na plus, it will be in contact with Cl minus, Cl minus. So in an ionic crystal, the coordination number you have to say for each type of ion. Here we say Na plus. The coordination number of Na plus is 6 here. 1, 2, 3, 4, 5, 6. In the previous case, the coordination number of that tetrahedral void is 4 because Zn2 plus is in contact with 4s2 minus ion. So in an ionic crystal, the coordination number means the number of oppositely charged ions which are in direct contact with that cation. Or if it is for cation, you have to see the number of anions touching on that cation. If it is for anion, if you are going for the coordination number for anion, you have to see the number of cations, those are touching that particular anion. So here the coordination number of Na plus, coordination number of Na plus is 6. So this octahedral void's contribution is 1 full. Let's see what are the other positions of this octahedral voids. So interior center is an octahedral void, and I'm going to say that each edge center, see, this is an edge center, this is an edge center, here this is an edge center, this is an edge, so this is the edge center, this is an edge, this is an edge center, here edge center, this edge center. Each edge center is an octahedral void because this will be in contact with a cation present here will be in contact with six anions. One here, one here, one here, one here, and one in the next unit cell and one in the next unit cell. So you have to extrapolate or extend this. You have to extend this towards the next unit cell. Similarly, you have to extend this line to the next unit cell. So next unit cell phase center atom will be in contact with this void. So this will be an octahedral void. Let's see what's that position. See, this is an edge. This is an edge. How many edges are there for this unit cell FCC? How many edges are there? There are 12 edges are there. Is 1 is the edge center, 2 edge center, 3 edge center, 4 edge center, 5 edge center. There are 12 edges for this unit cell, and this atom is not in this unit cell. It is the center of phase, front face of the next unit cell, which is kept over here. Similarly, this is also is the phase center of the next unit cell, which is kept in front of this unit cell. Now let's see this space, this void. This is again an octahedral void, which is in contact with how many Cl minus ion? 1, 2, 3, 4, 5, 6. So this is again an octahedral void, but this void's contribution is only 1/4 to this particular unit cell. 1/4 to this particular unit cell, because other 3/4 will be in the neighboring unit cells. Previously we saw this octahedral void here. Its contribution was full 1. Here this is full 1, but here only 1/4, because this unit cell is in contact with or in touch with other 3 unit cells. So this void or the Na plus which is present over here, it's only 1/4 is present in this particular unit cell, what I have shown here, and the other 3/4 will be in other unit cells. So the contribution is only 1/4 from the edge center, and there are 12 such edge centers are there. 12 into 1/4, that is 3, and here 1, that is one full. So one full is from here. So the number of octahedral voids will be 3 plus 1, that is 4. We know that the number of atoms present in this unit cell, number of atoms with which this crystal lattice or this unit cell is made, that is 4. There are 4 Cl minus. There are 4 Cl minus that we have already seen. There is a number of atoms with which this unit cell is made. So how many octahedral voids will be there? 4. Where are these 4 octahedral voids? One is at the center. Here, one is at the center, and 3 from this edge centers, what we have seen. So 3 plus 1, 4. These are the positions of this octahedral voids. So 4 atoms are there with which this unit cell is made, and there are 4 octahedral voids. 4 octahedral voids. What's the coordination number of this Na plus? Again, 6. It is in contact with 1, 2, 3, 4, 5, 6. Take care, this atom is not present in this unit cell. It is present in the neighboring unit cell, which is in contact with this shown unit cell. Similarly, you have to note this one also. This is again the phase center. This is situated at the phase center of the next unit cell, which is kept in front of this shown unit cell here. This one is present in this unit cell only. This is the central phase of this unit cell. This is the side center face of this unit cell, and this is the corner one of this unit cell. Only these two are in the neighboring unit cells. We have got this by extending this line in equal distance towards this direction. Same direction you extend. If this much length you take outside. If this is the length, almost that much length you take that side. So you can meet that center of the atom from the neighboring unit cell. So these are the positions of the octahedral voids. Uh, octahedral voids. So now look at this NaCl. NaCl. Na's coordination number is 6. What about the coordination number of Cl minus? What about the coordination number of Cl minus? So Cl minus coordination number, look at this Cl minus. With how many Na plus ions it's in direct contact? This is Cl minus. So here is one Na plus, interior center of this unit cell, edge center, see edge center Na plus, this edge center Na plus, top edge center Na plus. Every edge center there is one Na plus, but the contribution is only 1/4 to this particular unit cell. This is an edge center. So how many are in direct contact? How many are in direct contact? 1, 2, 3, 4, 5. And this is in contact with the interior center of the next unit cell, neighboring unit cell. Neighboring unit cell. So I'll be extrapolating this to the interior center of the neighboring unit cell. So this will be in contact with, means this will be in contact with the interior center of the neighboring unit cell. So 1, 1, 2, 3, 4, 5, and the sixth one is the interior center of the front unit cell that I cannot show here. So the Cl minus is also in contact with 6 Na plus. That means its coordination number is also 6. Na plus coordination number is 6. This one, see 1, 2, 3, 4, 5, 6. Na plus coordination number is 6. Cl minus coordination number is also 6. So we say NaCl, in NaCl, in NaCl, Na plus is to Cl minus is 6 is to 6 coordination. 6 is to 6 coordination means the coordination number of Na plus is 6, Cl minus is also 6. So in NaCl, each Na plus is in contact with 6 Cl minus, that is oppositely charged, and each Cl minus is in contact with 6 Na plus, oppositely charged. So in the case of an ionic crystal, the coordination number means the number of oppositely charged ions. NaCl is in 6 is to 6 coordination. Now, what is the number of NaCl in this? What is the number of NaCl? What is the Z value? What is the Z value? Z value. Z for simple cube is 1, body centered is 2, face centered is 4. What is the number of NaCl? If I consider it as a molecule NaCl, of course, for ionic solids, we have to say formula mass instead of molecular mass. Last year we learned we have to say formula mass. So, formula mass of NaCl, we know it is 58.5. That is a molar mass 58.5 grams. Na 23. Cl 35.5. So NaCl formula unit mass is 58.5. 58.5. So formula molar mass of NaCl is 58.5 grams per mole. But what is the number of NaCl together in this? What is the number of NaCl? You know that there are 4 Cl minus in this unit cell and there are 4 Na plus in this unit cell. In this particular unit cell, there are 4 Cl minus. How? The number of particles with which this unit cell is made, that is 4. And 4 Na plus. How 4 Na plus? We have seen one from the interior center and 3 from the edge centers. So there are 4 Na plus. So number of NaCl in this is Z value is 4. Z value is 4. So that's about the locating tetrahedral and octahedral voids in FCC. Now we are going for the density calculation. Density of an element or compound. Generally we can say density of the crystal lattice. Density crystal lattice is made up of unit cells. So what all qualities or specifications are there for unit cell? For example, taste, density, this all these characteristics are for the crystal lattice also. A big sugar crystal, the taste of it is same as that of the small unit cell of that sugar. Small unit cell of sugar's density is same as the density of the entire sugar crystal. So similar is the case with sodium chloride. Unit cell's density is same as that of the crystal lattice, big crystal lattice density. So density of crystal lattice. So for that we'll be going to find out the density of the unit cell. So here density of crystal lattice. Density of the crystal lattice is the density of the unit cell. Density we know in junior classes we have learned density is mass upon volume. Mass by volume. Now unit cell's mass means the mass of the atoms, number of atoms present in that unit cell. You consider a simple cube. In a simple cube, the number of atoms present is 1. I am showing the atoms here. Contribution is 1/8 from each. So, the number of atoms present, that is Z value is 1. If it is BCC, Z value is 2. If it is FCC, Z value is 4. That we have already learnt. Now, what is the mass of this unit cell? We know that only one atom is present. Only one atom is present. So mass of that one atom is the mass of this unit cell. Mass of one atom is the mass of the unit cell. So I'll be writing mass of this unit cell is mass of that mass of one atom upon volume of this unit cell. What is the volume if A is the edge length? That is A cube. If A is the edge